Mike Anderson. I'm an instructional technology consultant with Prairie Lakes Area Education Agency in Iowa.
I'm Scott McLeod, Director of Innovation for the AEA. Prairie Lakes serves about 45 school districts and about a dozen private schools in a geographic area about the size of New Jersey. We're a regional educational service agency that sits between the State Department of Education and our individual districts and schools. So today we're going to talk about what makes a quality STEM activity. We're going to highlight the importance of the design engineering cycle and go through a bunch of activities like robots and rockets and skimmers and whatever else we can come up with, just to kind of show you this stuff in action, and we'll sort of explain some things as we go along.
Yep. And we're going to put emphasis on the fact that we're not the traveling STEM carnival, right? We want to wrap this into learning, to deep understanding, to critical thinking, and not just be a one-and-done experience for kids to get excited about, but that has very little educational value to it.
Right, I think the challenge is that STEM stuff can be really cool, it can be fun, it's exciting, kids are engaged, they're enthusiastic, they go home and tell their parents. But like Mike said, we don't want to be carnies, right? We don't want to be like the carnival comes to town and it's fun and cool, but then you go away and like, okay, back to regular business. Like, STEM should really be a way of thinking, it should be a way of doing, a way of being. It should be connected to deeper learning material over time. It shouldn't just be a one-time event.
Right. It's a great chance for kids to inquire about the world around them and explore it through hands-on activities.
Right. So thanks for joining us today, or whenever you're watching it.
Tonight, today,
tomorrow. And we'll see you at the end. Thanks.
Thanks.
Here we'll see Colin engaging in the thrustwords activity, and the object here is to get the balloon to cross the distance on the fishing line. And so students have to come up with the device that will hold the balloon on the line and possibly carry passengers.
So, what I have here is just I taped a balloon on. And although I do fear that it's too much to one side, so it's going to kind of swerve, I do hope that the weight of this will balance it, though. And I think the most fun about making this was not trying to get it to go, but just making the initial design and all the useless features like the locking door.
So by now, Colin has realized that his device is probably too heavy to actually make it to the other end of the fishing line. It's got a lot of cardboard, a lot of tape, and but he's realized that as part of the design process, even before he even tested. And that sort of critical thinking about outcomes is what we want in kids.
Okay, Gabby, so you have a new design here. Why don't you tell us a little bit about it and what you changed?
First of all, I put fins on to kind of push the air kind of through that. Second of all, I put this in a different place. Before it was up here, now I put it down here.
Okay, let's take a look.
I didn't let it go at the right time, otherwise it would have been good. Wait, let me try again. I'll just pump it up.
Lucas is working on the skimmer task, and in this activity, students are asked to create what looks like a boat to go from the start line to the finish line. It could be based on time. It could also be based on how many passengers it can carry. In this case, it's carrying paper clips.
Okay, Lucas, you made some changes to your skimmer. Tell us about them.
Yeah, so I added just these because I thought they would help keep it from tipping over since it was falling towards the front and the sides. So I put like little rods to keep it stable there, and then I added this to keep passengers from falling off.
Oh, okay. So Lucas's design has failed, and he's now working on redesign like Colin had before. And that's what we want kids doing. We want kids testing out things, collecting data, getting feedback of some kind, and then redesigning. If we really wanted to get fancy, we could pull in an app like this one.
So here's a skimmer from a different time. So I'm going to hit play here.
This is a 3-sailed skimmer.
And it's on pressure right now, right? I'll go back to the smoke. So you can see the 3 sails right there. There we go. So you can see that first sail is the one that really harnesses most of the wind energy. And the next two a little bit. If I go to pressure, right, you see there's that red that's piled up against that back one. And then there's almost like a low pressure or vacuum here.
Right.
Afterwards.
Right. And okay, got it. And you can see there's a little push at the back and what looks also like a little bit at the front.
Yep.
For whatever that is. All right, cool. So again, you can see the vectors of the flow and the energy push and so on. Very cool.
Yep. So a very cool app. I think it's $2.99. Sometimes it's free. So
Thank you, Mike.
you're welcome.
Here we have kids making water rockets out of soda bottles. The goal is to get these things to launch and go high. Lots of opportunities here that you'll see as they're designing and creating for developmental open-endedness, depending on what their readiness is and what their interest is, where they can test out different designs and make them look the way they want.
So students are engaging in these activities. It's important for them to record data. So in the case of the water rockets, we had altimeters that would give us velocity, apogee, or the highest the rocket went. And students could then take this data and make decisions using it as far as when they went into the redesign stage. And then they would build and retest and take more data and just continue through this process.
And that data collection doesn't have to be fancy. We just mocked up a quick data table with chalk on the sidewalk.
Yep, it doesn't have to be a Google form on the iPad. You can just write it down on a piece of paper. The important thing is you're recording data so you can make decisions based on it.
But if you want to pull in the technology, they could obviously plot it and graph it using a spreadsheet program.
Absolutely, absolutely. Robots may be one of the first things you think of when you think of STEM. And they are a valuable tool because it gives students the opportunity to not only engineer a solution, but also have to program for a solution. Yeah, so this time we're using the gyro sensor, which is actually going to, what's the word I'm thinking? Oh no, it's gone.
It measures.
Yes.
Right.
It measures the distance, or it measures the angle that the robot is turned.
Okay, got it. All right.
Let's try it.
Okay. Notice that one of the things that's important here is the ability for Mike and I to interact and try this as adults, right, as educators. And so, you can't just hand these robots to teachers and expect them to do amazing things with them. They need the same kind of experiences and challenges that we've now set for ourselves, where we're saying, all right, let's make a track, let's see if you can navigate the track, let's understand how the different sensors work. So if you're doing any kind of robotics work with elementary teachers, they're going to need this hands-on play time, right, to figure out how this stuff works. Go ahead, Mike, you can set it going. Okay. Okay, so now we're on round 2, where we're asking the kids to do something a little more complex. So, Mike, what do we got going on now?
Okay, so now they have to program the robot to go the distance. So there are no sensors involved. So they need to program the robot to go the distance, and there's several ways to do that. And we're using rotations. So they had to figure out how far it is the distance, or the robot's going to travel. And then they also have to figure out how far around is it for one rotation. Right? And of course, that can be different depending on what wheels you're using. Okay, so for these wheels, they'd have to measure the circumference around. Okay, and then divide, and that's how many rotations they have to program into the robot, so it'll go that distance. So,
okay, so now would we have them just measure around the wheel, or could we do something like calculate it from the diameter or
right, so again,
the radius?
Depending on the age of the kids and what content that they're going to interact with in math, you could have them use the formula, you could have them just measure around. Robots are a ton of fun, I think that's clear, but we want to make sure we're pulling in meaningful learning too. And so, there's an opportunity here to pull in math in an authentic way, and we need to make sure we're doing that. Otherwise, this is sort of like a sideshow, just like we talked about. We don't want this to be a carnival. We want this to be a meaningful learning experience. The robots can take the role of rovers. During this STEM camp, students were asked to design a rover that could drive around the Mars surface and pick up dirt and take some measurements as they did so. They were not allowed to see Mars. They had to interact with it using a GoPro camera and a remote control for their rover.
So you gotta get where so you can see the volcanic acids.
At this table, ready to go.
Oh, sorry. I'm on the bridge. I'm going this way. Okay. Like I'm right there. I'm going that way. Okay. What's that? Oh, that's clear. Yeah, that's what I'm trying to do.
Notice how important collaboration is to all of this. These students have to work together, they have to generate ideas together, they have to bounce ideas off each other. There's no way that this is going to be successful if they're not working collaboratively to make this happen. They're testing ideas, they're brainstorming, they're identifying potential solutions, they're working together to make them happen. There's no reason that students should ever have to work in isolation in a rich STEM activity. We want them working together to solve problems, just like scientists and engineers have to do in the real world.
Right.
Yeah.
Hey, thanks for watching today. We know you're busy and we appreciate you spending a little time with us. We're just going to cover a couple things here at the end, just sort of reinforce some of the things we talked about throughout the video.
Yep, and one thing we want to hit is that STEM isn't necessarily always going to be strong in all four areas: science, technology, engineering, and mathematics. But there are certainly a few things we want to look for in every STEM activity, lesson, unit, whatever you may be doing.
So, for example, it better be hands-on, right? So if you're running kids through textbook chapters or worksheets and you're trying to call it STEM, you're sort of missing the point, right?
That's not STEM.
It should really be rich in terms of hands-on learning. Hopefully maybe it's got some inquiry in that. You know, that's what kids are looking for. That's where the enthusiasm and the engagement comes from.
Right. We also want to make sure that we're going through the engineering cycle and design thinking with multiple iterations. It's not enough just to go through once and have students create a skimmer or a rocket and then launch it and be done with it. They need to design, create, and then test, collect some data, and be able to go back and decide how they would redesign and rebuild and then retest it again. The more we can go through that cycle, the more rich that learning activity is going to be.
Right. Sort of drawing off the carnival point at the beginning of the video is that let's make sure that our activities, you know, they're fun, they're cool, but let's make sure they're connected to real learning, hopefully some deep important concepts, not just minutia, and that kids really get a chance to immerse themselves in math and science and engineering in ways that maybe mirror, at least as much as possible, what scientists and engineers and mathematicians do in the real world.
Yep. We also want students to be working in groups so they can collaborate. And then we want them thinking about how they can communicate out their work. We don't want this to be an individual activity because in the real world, engineers work together to accomplish tasks and to build and to, yeah. Ran out of gas. And we can add a lot of motivation to whatever we're doing if we make it problem or challenge based. So if we throw out at the students that they need to create something, there's a problem, how can we fix that problem? How can we design something that will achieve a solution to a challenge? That'll push them to discover, to critically think, to collaborate with others in order to accomplish that task.
Right. So give them some kind of goal orientation. Don't let it just be something that you do in isolation, something that's decontextualized. Give them something to strive for.
Yeah, and whenever possible, we want that to reflect the real world, what engineers are doing in the real world too. So keep that in mind too.
Mm-hmm. Let's see what else is on our list. You can use tech appropriately and creatively throughout the process. So you can use it for capturing and recording data, plotting it out, charting it out. You can use it for sharing out to the public. So you know, it's a great way to capture process, some pictures, video, electronic writing to accompany whatever you're doing. They're hands-on in the room.
Yep. Have them capture their prototype in action so they can reflect back on it. Sometimes when we have students, send their skimmer down the aisleway, right, or launch their rocket, and then we go back and ask them questions about it, they can't really remember everything that happened. So if we can record that and then we can show them back, sometimes some learning will come out of that. And then when they go back to the redesign piece, it's a lot more rich.
Right. Photos are a great way to have them explain their designs or explain something that happened during the process where they can label it or voice narrate it or something like that.
Also, we want to make sure that these are developmentally open-ended with lots of choice and agency for students. So, for instance, you probably noticed with our skimmer activity, we had lots of materials out. We don't want to limit their choices as to what they can build their skimmer out of or build a rocket out of or whatever they may do. We want to make sure they have plenty of choice, plenty of options to try out.
So, Mike, you want to talk? Let's end with the process.
Sounds good. So, as they're creating things, as they're designing things, it's really not about the product they're making. It's more about the process they're going through. And we've talked sort of this whole session, this whole video about the engineering process and going through those steps. And that's where the richness of STEM lies. That's where the power of it lies, is going through that, collaborating. That's where we're going to uncover those conceptual understandings that we want. And so we really want to focus on the process. And you saw the skimmers we made were not very good, right? But the learning that happened through creating those, that's where that power lies.
So be sure you capture that process.
Right.
Okay, thanks for joining us. Our contact info follows. Be sure to get in touch if you have any kind of questions or you want to share your own stories or anything else that you want. We'll be glad to chat. Thanks.
See ya. Dream big.